by here. I'm here standing on the earth. Force of attraction acting between the earth and you and me everywhere. There is a force of attraction again here to see the second video for the gravitation again. Let's continue. To recall the topics last time covered, we had done with how the moon is associated with a certain force with the earth. We defined it as the force of gravitation. Also we told about the gravity as not only action force between the surface objects of the earth and the earth, but the force of acting between or attraction between any two particles, any two objects in the universe, thus called as a universal force. So again we saw the movement of this moon along the axis of this earth due to certain force of attraction between them, which was aligned by the straight line joining the centers of the the two masses, and also the changing velocity, how it was acquired due to the force only called as gravitational force. So due to this force, it is the universe that is bound together with each other. I told you a glimpse that we will see if there would have no such force acting between any body. So such as the stone rolling on a string in a circular motion, if we stop applying the force, the stone will collapse in the middle. Same way, the universe would have collapsed in the same way, certainly due to the absence of this gravitational force between any two objects. Also, the velocity which was there in the moon or any celestial body, which is responsible for the movement around the planet, is known as the critical velocity, which will be deriving it later on. So the force again was, and the movement was again correlated with something that was called as centripetal force. Centripetal force. So this was the force we had seen, which was responsible for the movement of planets around the sun or the satellites around the planets. So this centripetal force was done. We saw different examples for that. To continue with it now, we'll see how this planetary motion, that is the concept of this planetary motion, which was studied and introduced by many scientists since the last decades. Okay, the Greeks were the philosophers who at that era observed all these things, all these phenomena with the naked eyes. Okay, and now since the last decades till now at present, whatever new upcoming scientists came up, discovered new theories. Now the work is more being specially made easier by the use of satellites. Okay, so we'll deal about all this planetary motion right from then. It was Johannes Kepler. During that time, he discovered, before the discovery for Newton's laws even, planetary motion was studied by him just by the naked eyes, by observing the movements of the planets around the sun. And this led him to define some laws, though he could not define exactly why the planets follow these laws. Still, he postulated some theories. He stated 3 laws known as Kepler's laws, which we'll be studying with an example now here. Now we know, so let's study about this topic today, that is Kepler's laws of planetary motion. So here we know that every object around the earth is associated with the planet with some force, centripetal force, or we'll call that as gravitational force. Here also, each and every planet, let's visualize with the help of sun. Our solar system, sun is a star around which all the 8 planets are revolving. Kepler noticed that the direction and the motion of each of these planets was peculiarly different. We just know that a planet will revolve around the star along a certain orbit, which will not overlap the orbit of any other planet. Also, we know that this definite path, the revolutionary speed and the time required by each planet is different. Here, considering for it that is the Earth and the Moon, if we see, this theory led by Kepler states that the orbit in which the planet moves around the sun is not just circular but it's elliptical. Ellipse. What is an ellipse? Ellipse can be studied if you know about frustum. We studied in maths. A cone. We cut this cone with an inclined plane. This inclined part will be known as an ellipse. Okay, ellipse has two focal points. That is two foci. I say F1 and F2 suppose, such that any point on the ellipse. Okay, the line joining any point. Suppose point A. This line joining point A F2 and A F1. The sum of these two lines joining the point A will be equal to the sum of lines joining to point B, such as AF1 plus AF2 is equal to BF1 plus BF2. This sum is same. So that gives us a theory of an ellipse. What is an ellipse? With two focal points. So here we need to study that the Earth or the other planets around the sun, they are not moving in a circular orbit, but rather they are moving elliptically. Okay, so this is the ellipse with one foci. Suppose at one of focus I place the body that is called as the sun, and at any point randomly at A or B or C, we'll say this point may be defined as Earth. So this motion of Earth around the sun is elliptical way. The orbit is elliptical. So this line joining the sun and any point on the ellipse, this defines the circular orbit or the elliptical orbit of the revolution pattern of Earth around the sun. To visualize this, Kepler's model is the best way to understand. Here I'll try to demonstrate this type of models, Kepler's model. Here I've taken a stretch without a sling, cloth tied upon a vase. I put up at the central solar system, that is the sun, suppose in the center. Now this sun is exerting a force of attraction on all over the planets revolving around it. Okay, so there is a certain force of attraction by the sun on whatever revolving objects around it. Okay, so this is the sun part. Suppose I take a planet, suppose just observe, try to observe the way the marble or the planet is moving around this sun. Okay, so I move out here in circular orbit, just observe the way. Got it? Did it move in an exact circular way? No. Observe it again. Okay, this is the sun and this is the movement. Now again, so it moved elliptically. Okay, so it was creating an elliptical way of revolutionary pattern. Okay, maybe it too also what it may be, each and every planet has different mass and different types of structures which will be moving randomly around the sun in different ways. So equal masses show equal way of orbiting pattern, but certain different marbles. You can take up this example with certain different types of masses, with different masses, and the marbles will be moving along the orbital patterns in different way if their masses differ from each other. So let's concentrate upon. So this elliptical orbit, what was said by Kepler, was seen to be revolving pattern of the Earth around the sun, or the planet around the sun. Here Kepler states some laws. So in short, to understand the law, firstly he states that the line or the orbit or the revolving pattern of a planet around the sun is not circular but rather elliptical. Okay, first law states that the orbit of planet around the sun is elliptical. This is the important point. It's an ellipse. Secondly, we'll understand the required speed of the planet around the sun is different for different planets we have studied previously. Here we'll see that if the planet, suppose point A to point, suppose P here, is moving from this point to this point on the ellipse. Same way, we take a point Q over here, B to Q, and C to R, suppose. So, second law states that the area swept by this line, I name it S as the sun, point S. Point SA is sweeping certain area. Okay. This is the area swept by line AS till P. So the area ASP will be always equal. Will be always equal to the area swept by point BS, line BS till Q. This equal area. So I say area BSQ. Here, area swept by AS in certain interval of time will be equal to the area swept by line BS in certain equal area in equal interval of time. So, second law stated by Kepler states that the line joining, what is this AS exactly? The line joining the planet and the sun. What is BS here? The line joining the planet and the sun. Line joining the planet and sun sweeps equal areas in equal interval of time. So that's it as second law. The line joining the planet and the sun will sweep equal distances in equal area interval of time. So this is the second law stated by Kepler. So in this case, this area is equal to this area is equal to this area. Certainly, you will see if equal interval of time, you can understand something. You will see the distances AP, BQ or CR. Are they equal? No, not of course. Okay, so certainly the time required is same. To see this area, the time required from A to P, B to Q and C to R is same. But we see that the distance is not same. What do you infer from this? Of course, that in this interval of time point C to R, certainly, do you think about it? The speed of the planet will be comparatively greater than the speed from points B to Q. Okay, think about it properly. So, second law, that is the second law about it. Moving on to the third point. The third law states the constant law. The law of constant, that is the time. Again, we are dealing with the time now here. The time required is certainly different. In this area slot, this area slot, and this area slot, the time required is different. Means the speed of the planet is changing at all these three different points. So, here the time period, we will call it as the time period required by the planet to revolve around the sun. This will be certainly different. So let's discuss the time period be T. Time period of revolution be T, and the radius. What is the radius exactly here? The line joining the sun and the point, that is of the planet. This radius. Now this radius is different, this is different, this is different. So here we talk about the average radius. Okay, average radius. What is the average radius now? Average of this distance, and this distance. So whatever the average distance will be there, okay, let's define it as R. R is the average distance between the planet and the sun. The third law of Kepler states that the square of the time period of revolution of a planet around the sun is directly proportional to the cube of the average distance between the planet and the sun. So that implements T square is proportional to R cube. Okay, so this is the statement, this is the relationship between the time and the distance between the planet and the sun at every point on the elliptical orbit. Your T square proportional to R cube, that is relatively said as T square by R cube will be constant. This term K, it is defined constant term by K. So these are the three laws stated by Kepler for the planetary motion. Though Kepler was not able to tell perfectly that why these planets follow this law. Okay, the later on discoveries done by Newton will be leading us to appropriately tell the distance and the relationship between the force of gravitation between these two objects, and that will be verified by Newton's universal law. Your Kepler was responsible somewhere to lead the discovery for the planetary motion of the planets around the sun. Okay, so these are the laws. So today, again continuing with the topic, we studied first of all with the centripetal force, that we defined gravitation between two objects, and here Kepler's laws were stated by Kepler. To learn these laws by heart, understanding the phenomena and the principle of elliptical orbits, you can just demonstrate yourself and study, go on exploring your study with the Kepler's model. That can be a presentation topic, and you can go on with the queries for these types of questions. Now, how Newton will carry out his theory, his laws based on this Kepler's third law will be continued in the next period. Here to concentrate upon the topics Kepler's law of planetary motion for today's topic. Fine with it? Okay. Let's continue with the topic again. The set of questionnaire is given to you after the first lecture, and now previously you'll be getting the questions and the queries. Any of the queries can be asked with all of your questions. Go on with the exploring of the topic along with the practical performance, and let me tell you one thing. Think about it. The seasons what we suffer, that is suppose summers. The hot object is the sun. If we are near to the sun, we'll be suffering summers, and if we are farther from the sun, we'll be suffering from winters. What do you think about this statement? Think about it. Try to discover your own theories and think about it and let me know about it. Let's discuss this topic again. Is the Kepler's model responsible for the seasons what we suffer the year round or not? Think about it. Thank you for today.